Using fusible safety switches introduces a potential issue, which is increased tripping risk. The fuses in the safety switches could trip prematurely, even under normal operating conditions, causing unnecessary interruptions to the motors. This is because the fuses will respond to both overload conditions and short circuits, while the circuit breakers in the motor control center are designed specifically for short circuit protection. If proceeding with fusible safety switches, they should be sized appropriately to provide protection against the maximum current that the motor can draw. This can be determined from the motor's rated full load current, or FLA. Select a fuse that has an ampacity of 125% to 150% of the motor's FLA. If fusible safety switches are used, consider the following consequences. Firstly, increased downtime. Premature fuse tripping can result in longer downtime for maintenance and troubleshooting. Secondly, slower response time. Fuses generally have a slower response time than circuit breakers, which can lead to potential damage to the motor or equipment if a fault occurs. Thirdly, inconvenience. Fuses need to be replaced after tripping, which can be inconvenient and time-consuming. Based on the potential issues and consequences outlined, it is generally not recommended to use fusible safety switches downstream of motor control centers with circuit breakers for short circuit protection. Non-fusible safety switches are typically the preferred option in this scenario. If the fusible safety switches have already been purchased, consider the following alternatives. Firstly, replace them with non-fusible safety switches. This is the safest and most reliable option. Secondly, use auxiliary contacts from the circuit breakers in the motor control center to control the safety switches. This will ensure that the safety switches only trip when a genuine short circuit occurs. Thirdly, install current-limiting fuses downstream of the safety switches. This can help prevent nuisance tripping, but it is not as effective as using non-fusible safety switches. When dealing with motor control centers, or MCCs, and motor protection, understanding the role and proper application of safety switches is crucial. An MCC is essentially an assembly of motor starters, feeders, and control devices, all housed in a single enclosure. Each motor within the MCC is controlled by a motor starter, which includes a contactor and an overload relay or electronic overload. The contactor is an electrically controlled switch used to energize or de-energize the motor, while the overload relay protects the motor from excessive current draw that could cause it to overheat and fail. Short circuit protection, or SCP, is typically provided upstream of the motor starter by a circuit breaker or fuses. This protection is designed to quickly interrupt the circuit in the event of a short circuit fault, preventing damage to the equipment and minimizing the risk of fire or electrical shock. A safety switch, also known as a disconnect switch, is a manually operated switch used to isolate a motor from its power source for maintenance or repair purposes. It provides a visible break in the circuit, ensuring that the motor is energized and safe to work on. Safety switches are available in both fusible and non-fusible types. A fusible safety switch incorporates fuses within the switch mechanism, providing overcurrent protection in addition to the disconnecting function. A non-fusible safety switch, on the other hand, only provides the disconnecting function and relies on upstream overcurrent protection devices, such as circuit breakers or fuses, to protect the motor and circuit. In a typical motor control center installation, non-fusible safety switches are commonly used downstream of motor starters that already have short circuit protection provided by circuit breakers or fuses in the motor control center. The circuit breakers are sized to protect the motor branch circuit conductors and the motor itself from both short circuit faults and overload conditions, while the overload relay in the motor starter provides additional protection against running overloads. The non-fusible safety switch simply provides a convenient and safe means of disconnecting the motor from its power source for maintenance or repair. When fusible safety switches are mistakenly ordered or considered for use in this type of application, several potential issues and consequences must be taken into account. The primary concern is the increased risk of nuisance tripping. Fuses are designed to protect against both overloads and short circuits, and they will trip whenever the current exceeds their rated ampacity for a certain period of time. In a motor circuit, fuses may trip prematurely due to normal motor starting currents or temporary overloads. even if the circuit breaker in the motor control center is properly sized to handle these conditions. This can result in unnecessary downtime and inconvenience, as the fuses must be replaced before the motor can be restarted. Another consideration is the slower response time of fuses compared to circuit breakers. Circuit breakers are designed to trip very quickly in response to short-circuit faults, typically within a few milliseconds. Fuses, on the other hand, may take longer to trip, especially for low-level overload. This slower response time can potentially lead to greater damage to the motor or other equipment in the event of a fault. In addition to the potential for nuisance tripping and slower response times, fusible safety switches also require the stocking and replacement of fuses, which can add to the overall cost and complexity of the installation. Fuses must be properly sized to coordinate with the circuit breakers in the motor control center and the motor overload relay to ensure that the correct device trips under different fault conditions. If fusible safety switches are used, the fuses should be sized based on the motor's full load current, or flaw, as indicated on the motor nameplate. The National Electrical Code, or NEC, provides guidelines for sizing fuses for motor circuits in Article 430. In general, the fuse ampacity should not exceed 175% of the motor's FLA for inverse time circuit breakers, 225% for time delay fuses, and 300% for instantaneous trip circuit breakers. However, the specific requirements may vary depending on the motor's design and application. It is important to consult the NEC and other relevant standards to ensure that the fuses are properly sized and coordinated. If the fusible safety switches have already been purchased, there are several alternatives to consider. The best option is to replace them with non-fusible safety switches. This eliminates the risk of nuisance tripping and ensures that the circuit breaker in the motor control center provides the primary short circuit protection. Non-fusible safety switches are readily available and relatively inexpensive, making this a cost-effective solution. Another option is to use auxiliary contacts from the circuit breakers in the motor control center to control the safety switches. Auxiliary contacts are small switches that are mechanically linked to the circuit breaker mechanism. They can be wired to the safety switch control circuit to ensure that the safety switch only opens when the circuit breaker trips due to a short circuit fault. This prevents the safety switch from tripping prematurely due to overloads or motor starting currents. A third option is to install current limiting fuses downstream of the safety switches. Current limiting fuses are designed to quickly interrupt high fault currents, limiting the amount of energy that flows into the circuit. This can help prevent nuisance tripping of the upstream fuses in the safety switch. However, current limiting fuses are more expensive than standard fuses, and they may not be as effective as using non-fusible safety switches. In summary, when using motor control centers with circuit breakers for short circuit protection, non-fusible safety switches are generally the preferred option. Fusible safety switches can introduce potential issues such as nuisance tripping, slower response times, and increased costs. If fusible safety switches have already been purchased, consider replacing them with non-fusible switches, using auxiliary contacts from the circuit breakers, or installing current limiting fuses downstream of the safety switches. Always consult the NEC and other relevant standards to ensure that the motor circuit is properly protected and coordinated. Understanding the principles of motor protection and control is essential for ensuring the safe and reliable operation of electrical equipment. By carefully considering the various options and following industry best practices, electrical engineers and technicians can design and install motor control systems that meet the specific needs of their applications. Motor control centers, or MCCs, are a common sight in industrial and commercial facilities, providing a centralized location for controlling and protecting electric motors. These motors power a wide variety of equipment, from pumps and fans to conveyors and compressors, making them essential to many industrial processes. The design and installation of motor control systems require a thorough understanding of electrical codes, standards, and best practices. The National Electrical Code, or NEC, is the primary standard for electrical installations in the United States, providing detailed requirements for conductor sizing, overcurrent protection, grounding, and other aspects of electrical safety. Other relevant standards include those published by the National Electrical Manufacturers Association, or NEMA, and the Institute of Electrical and Electronics Engineers, or IEE. NEMA standards provide guidance on the design, construction, and performance of motor control equipment, while IEE standards address topics such as power system protection and coordination. In addition to these standards, it is important to follow industry best practices for motor control system design and installation. These practices include selecting appropriate components, properly sizing conductors and overcurrent protection devices, providing adequate ventilation for motor control center enclosures, and implementing effective grounding and bonding techniques. It is also important to consider the specific requirements of the application when designing a motor control system. Factors such as the motor's horsepower, voltage, and full load current, the type of load being driven, the ambient temperature, and the presence of hazardous materials can all affect the design and installation of the system. Proper motor protection is essential for preventing motor failures and ensuring the safe and reliable operation of electrical equipment. Motor protection devices include overload relays, short-circuit protective devices, and ground fault protective devices. Overload relays protect motors from excessive current draw that could cause them to overheat and fail. These relays typically have an inverse time characteristic, meaning that they trip faster for higher levels of overload. Short-circuit protective devices, such as circuit breakers and fuses, protect motors and branch circuits from short-circuit faults. These devices are designed to quickly interrupt the circuit in the event of a short circuit, preventing damage to the equipment and minimizing the risk of fire or electrical shock. Ground fault protective devices protect personnel from electric shock hazards caused by ground faults. These devices detect leakage current flowing to ground and quickly interrupt the circuit, preventing dangerous touch voltages from developing. Proper coordination of motor protection devices is essential for ensuring that the correct device trips under different fault conditions. Coordination studies should be performed to determine the appropriate settings for overload relays, circuit breakers, and fuses to minimize downtime and prevent unnecessary equipment damage. In addition to motor protection, motor control systems also include control devices such as push buttons, selector switches, and pilot lights. These devices are used to start, stop, and monitor the operation of motors. Programmable logic controllers, or PLCs, are often used to automate motor control functions and provide advanced control features such as sequencing, interlocking, and PID control. Variable frequency drives, or VFDs, are used to control the speed of AC motors. VFD can provide energy savings by reducing motor speed to match the load requirements. They can also improve process control and reduce mechanical stress on equipment. The installation of motor control systems requires careful attention to detail. Conductors must be properly sized and terminated, and enclosures must be properly grounded and bonded. All wiring must be neatly organized and labeled to facilitate troubleshooting and maintenance. Motor control centers should be located in clean, dry environments with adequate ventilation. The enclosure should be protected from physical damage and corrosion. Regular maintenance is essential for ensuring the continued reliable operation of motor control systems. Maintenance tasks include inspecting and testing circuit breakers and fuses, cleaning and lubricating contacts, tightening connections, and checking for signs of overheating or corrosion. Motor control centers should be inspected regularly for signs of damage or wear. Any damaged or worn components should be replaced promptly. In conclusion, motor control systems are an essential part of many industrial and commercial facilities. The design, installation, and maintenance of these systems require a thorough understanding of electrical codes, standards, and best practices. By following these guidelines, electrical engineers and technicians can ensure the safe and reliable operation of motor-driven equipment. Consider a scenario where you have a motor control center, or MCC, that feeds several motors in an industrial plant. Each motor is critical to the operation of a specific process, and any downtime can result in significant production losses. To minimize downtime, you want to ensure that the motor control system is designed and installed to provide reliable and robust performance. In this scenario, you would start by carefully selecting the appropriate components for the motor control system. This would include selecting circuit breakers or fuses with appropriate interrupting ratings, overload relays with the correct trip characteristics, and conductors that are sized to handle the motor's full load current and starting current. You would also want to consider the ambient temperature and the presence of any hazardous materials when selecting components. Next, you would perform a coordination study to ensure that the motor protection devices are properly coordinated. This would involve determining the appropriate settings for overload relays, circuit breakers, and fuses to minimize downtime and prevent unnecessary equipment damage. You would also want to consider the potential for ground faults and implement ground fault protection if necessary. During the installation process, you would pay close attention to detail to ensure that all conductors are properly sized and terminated, and that all enclosures are properly grounded and bonded. You would also want to neatly organize and label all wiring to facilitate troubleshooting and maintenance. Once the motor control system is installed, you would implement a regular maintenance program to ensure its continued reliable operation. This would include inspecting and testing circuit breakers and fuses, cleaning and lubricating contacts, tightening connections, and checking for signs of overheating or corrosion. By following these steps, you can ensure that the motor control system provides reliable and robust performance, minimizing downtime and maximizing production. The electrical system supplying power to the MCC must also be considered. This includes the upstream protective devices, transformer size, and available fault current. Ensuring the electrical system can handle the load and fault current is important for proper system operation. Load calculation should be performed to determine the total demand of the MCC, including all motors and other loads. This calculation should take into account the diversity factor of the loads, which is the probability that all loads will not be operating at their maximum demand simultaneously. The transformer supplying power to the MCC should be sized to handle the total demand of the MCC with some margin for future expansion. The available fault current at the MCC should be calculated to ensure that the circuit breakers and fuses have adequate interrupting ratings. The interrupting rating of a circuit breaker or fuse is the maximum fault current that the device can safely interrupt without failing. If the available fault current exceeds the interrupting rating of the protective devices, the devices may fail during a fault, resulting in damage to the equipment and potential hazard. The grounding system for the MCC is also critical for safety and proper operation. The grounding system provides a low impedance path for fault current to return to the source, allowing the protective devices to quickly interrupt the circuit in the event of a fault. The grounding system should be designed and installed in accordance with the National Electrical Code, or NEC, Article 250. Surge protection devices, or SPDs, can be installed at the MCC to protect sensitive electronic equipment from voltage surges caused by lightning strikes, utility switching, and other events. SPD diverts surge current away from sensitive equipment, preventing damage. The selection and installation of SPD should be based on the recommendations of the manufacturer and the requirements of the application. Proper labeling of all components in the MCC is essential for safety and efficient maintenance. All circuit breakers, fuses, starters, and other devices should be clearly labeled with their function and rating. Wiring diagrams and other documentation should be readily available for troubleshooting and maintenance. Regular training of personnel who operate and maintain the MCC is important for ensuring safe and reliable operation. Training should include topics such as motor control principles, electrical safety, troubleshooting techniques, and maintenance procedures. Personnel should be trained to recognize potential hazards and to take appropriate action to prevent accidents. Commissioning of the MCC is the process of verifying that the equipment is properly installed and functioning correctly. Commissioning should be performed by qualified personnel and should include testing of all components and systems. A commissioning report should be prepared to document the results of the testing. Retrofitting an existing MCC can be a cost-effective way to upgrade the equipment and improve performance. Retrofitting may include replacing old circuit breakers with new ones, adding variable frequency drives, or upgrading the control system. When retrofitting an MCC, It is important to ensure that the new equipment is compatible with the existing equipment and that the installation is performed in accordance with the National Electrical Code, or NEC. Energy efficiency should be considered when designing, installing, and maintaining motor control systems. Variable frequency drives can be used to reduce motor speed to match the load requirements, resulting in energy savings. High-efficiency motors can also be used to reduce energy consumption. Lighting in the MCC room should be energy efficient, such as LED lighting. Remote monitoring of the MCC can provide valuable data on system performance and energy consumption. This data can be used to identify potential problems and to optimize system operation. Remote monitoring can also be used to provide alerts when abnormal conditions occur. Safety interlocks can be used to prevent accidental operation of equipment. Safety interlocks are devices that prevent a machine from starting if certain conditions are not met, such as a guard being in place. Safety interlocks can also be used to shut down a machine if a hazardous condition is detected. Arc flash studies should be performed to determine the potential arc flash hazard at the MCC. An arc flash is a dangerous electrical explosion that can occur when a fault occurs in electrical equipment. Arc flash studies can be used to determine the level of personal protective equipment, or PPE, that is required to work on the equipment safely.